So the two papers are ENARSI and then ENCORE. First we are going to begin with ENARSI because this has got more deep dive. So most of the topic when I cover in ENRSI, it is also getting covered in ENCORE. Say for example OSPF, EIGRP, those things are also there in ENRSI. This is not only just configuring, it is also troubleshooting. This is more deep dive. So when I start with ENARSI, parallelly we also cover majority of ENCORE paper. That's why I would like to start from ENARSI. So we begin with layer 3 technologies, configuring and troubleshooting. I'll also be covering something which is not in the syllabus called using Wireshark. Do you use Wireshark?
I have before.
Do you use it daily?
Not daily.
Okay. It's a very important and nice tool for troubleshooting. So then and there I'll be showing you some tips of how to use the Wireshark effectively. Recently, maybe less than 3 months, I delivered a training on Wireshark for US Air Force. So it was very nice, interesting, and I delivered for US Air Force 1 week of training. So I'll not be teaching you as one full week of Wireshark. I'll be using Wireshark and teaching you then and there, in bits and pieces, which you can put together. Fine. So we are going to begin with layer 3 technology. Troubleshooting layer 3 technology, not only with some debug commands and show commands, we will also be using Wireshark. That's why I use the topic Wireshark. Followed by EIGRP, the Cisco's routing protocol, configuring and troubleshooting it, and the BGP as a routing protocol to connect to the internet. The border gateway protocol is to bring the network from the internet into the enterprises. So we are going to see BGP and also connecting remote sites with Cisco DMVPN. DMVPN, Dynamic Multi-Access VPN. It's an IPsec security VPN which we are going to use to connect to multiple remote sites in a secured way. Have you done any security VPN earlier?
No, sir, I haven't.
Okay, then we have to start from very basic. Straight away we will not be getting into DMVPN. I'll start from site-to-site VPN. I have to teach you IKE, ISAKMP and crypto, and then we will get into DMVPN. So in between, between this topic and this topic, we have a lot to learn which is not mentioned here. Next is optimizing EIGRP, and then securing and managing. This all comes under the same topic, DMVPN, and then using IPv6 in EIGRP. IPv6 is one of the important topic for our current and future. So you will see in every section IPv6 will come. See here also IPv6, monitoring network using IPv6, but this is for OSPF and with MPLS and so on, whereas the previous one is for EIGRP with DMVPN. So the last topic on every section will be monitoring network using IPv6. So the VPN technology, I also introduce you here the VPN technology before entering into DMVPN. So it's going to be a kind of recap, and then we'll get into OSPF, and then earlier we learned BGP, bringing internet to the enterprises. That is incoming. Now we are going to see the outgoing, the upstream ISP using BGP, and also we will be learning layer 3 MPLS VPN. See, MPLS VPN and the VPN which we learn here in this first section is totally different. They are not same. When we say VPN, it's virtual private network. It's private network. There is nothing related to security. So VPN is a general term. See, the first section we learn the security VPN. In the second section also we learn VPN, but this is not security VPN. This is just label switching, MPLS layer 3 VPN. But if you want to know this MPLS layer 3 VPN, we should first learn MPLS. So that is what filling the gap in between these two. It is not mentioned here in the course content, but you will be covered with the MPLS first, very deep dive on MPLS, then we will get into MPLS layer 3 VPN. And then high availability means like redundancy for LAN clients and so on. And then again using OSPF to route IPv6 packets, followed by a new design in data center, today's data center, called leaf and spine architecture. Have you heard about this leaf and spine design anytime ever before?
During my CCNA studies.
Okay, so leaf and spine is a new approach, but when I say new, it is not very new. It's there for at least 10 years now. Leaf and spine architecture, but it gained popularity very recently. This is like east to west communication. When we take a classical network design, we have a access layer, we have distribution layer, and we have core layer, which is north to south or south to north communication, whereas leaf and spine is east to west or west to east communication. This is horizontal. The traditional network design is vertical. So this is more effective. Leaf and spine architecture is more effective design compared to the vertical design, access, distribution, and core. Right? And then overlay concepts, nothing but IPsec VPN, which is also covered in section 1 for DMVPN. OSPF area types. See, OSPF is coming here and OSPF is in the previous. So what I'll do is when I deliver, I'll try to put all the OSPF in every section in one continuous series of learning, instead of jumping, leaving OSPF in the middle and taking some other topic like MPLS and then again coming back to OSPF. That may not be that nice approach. So what I'll do is, if I start EIGRP, I'll cover the complete EIGRP, and likewise OSPF, BGP, MPLS. See here, BGP is also scattered. In the original course content, they have scattered here and there. It is here in the section 3, it is also here in section 2, it is also here in section 1. Yeah. So I'll try to put all in one series so that it will be easy for us to complete every topic from beginning to end. Right, leaf and spine architecture. Overlay, underlay means overlay is nothing but the encapsulation, the tunnels. VPN, nothing but VPN. Right, area types. When we say area type, it talks about stub in OSPF. When we go there, we'll talk. So, scaling BGP with site using internal BGP. I'll talk about this IBGP later when we go. At last, see again IPv6 comes in the picture. And there is something called DNA. And that's a monitoring tool which we have. And then we have IPv6. I think this should be a separate bullet. IPv6. So we'll go deep into IPv6, very interesting one, the complete IPv6. And then we'll start QoS, and then QoS on the campus, Internet Edge, WAN and MPLS. See, these are things that we learned from the first chapter, like Edge, WAN, MPLS. So how QoS is implemented in all this area, how it is implemented inside the enterprises, in the edge, over the WAN, in the MPLS, how QoS is implemented. So we learn QoS here and we see how to implement it in different part of our network. So that brings us to the end of ENRSI. ENARSI. These are the things that we are going to cover. And comes the ENCORE. In ENCORE, same OSPF, EIGRP, BGP, NAT, which was not covered earlier, we cover here. This is not a new syllabus for you. For those who have done CCNA, you know very well these things. We'll have a recap of VLAN, trunking, spanning tree protocol. I think this ENCORE will be an easy one for you. Only the challenging is ENRSI. So when we cover ENRSI, major topics of ENCORE will be covered and the other topics will be well known. Whichever we don't cover in ENRSI, those topics are again not new topics, they are well known topics. We'll see. Then we'll also see introduction to SD-WAN, programmability. See, the same quality of service is also here. A little bit introduction to wireless also we will see. Yeah. So these are the topics that we have for this course. Later you please go through this, and if you have anything to say, you can say in the next class. Yeah. That's why I have sent you. So today I'm going to just again use this day for understanding your knowledge on routing. I'm not going to get into the first chapter of this course. I'm not going to do that now. Before that, I need to understand you, your background, your understanding in these topics in CCNA level you learned. I want to see how much you have learned, so that we can start properly from the right phase. Previous class also I tested in the very basic level. Now this is second level, like the topics that we just saw in the Word file. Related to those topics, I'm going to have a small questionnaire now. Are you ready? Shall I ask you some questions? Will not be too tough.
Sure.
Alright. Now when we talk about routing protocol, we can classify this routing protocol into two categories. One is IGP, another one is EGP. Can you name some IGP protocols?
RIP.
Correct. Routing Information Protocol.
ISIS.
Intermediate system to intermediate system.
EIGRP.
Enhanced Interior Gateway Routing Protocol.
I want to say OSPF.
Open Shortest Path First. That's all. There is nothing more than this. And for EGP, the only protocol we have is Border Gateway Protocol, BGP. So that's the only protocol for EGP. BGP is the only protocol we have as a external. IGP is interior, EGP is external gateway protocol. The only external gateway protocol between the borders what we have is BGP, Border Gateway Protocol. Excellent. Now we have these many protocols. Why we need these many protocols? The routing protocols purpose is to provide us the route to reach destinations. That's the main purpose of any routing protocol, whether it is BGP or ISIS. Routing protocol should provide us the route information, the path information to reach various destinations. Then why I need these many protocols? Do you have any answer? We need just the destination, path to destination. Then why we need these many protocols? One protocol is enough. No. Why we have these many?
I believe it's for optimization. So each protocol has a benefit. What they're used for, maybe to increase bandwidth or throughput, better evaluation of a hop count. It varies in their dependency.
Right. So every protocol has got its own method of finding the best path. You gave an example. RIP uses hop count, OSPF uses bandwidth. Likewise, every protocol has got its own way of finding the best path. Now, whichever suits our policy, whichever suits our requirement, we pick that protocol, enable it in our device, and get the path selected as per our policy. That's a good answer. So we have protocols doing same job but in a different way. We may not like the way that RIP finds the path, but we like the way that OSPF finds the path. So we can enable OSPF instead of RIP. Sometimes the other person may not like OSPF, he likes the hop count. So he likes RIP to be enabled. So it depends on the requirement, depending on the policy, depending on the requirement, we pick any one of this. That's why we need this many protocols. So there is no protocol bad. Every protocol is good when it is enabled in the right place. RIP is also a very good protocol when you are focusing only on the hop count. See, if we are talking about tunnels, we will focus on we will like the protocol which focuses on the hop count. Tunnel is one hop. Tunnel may be between the first router and the 100th router, but the tunnel will cover all those 99 routers. See, if I have edge 1, edge 2 router, in between I have a very big internet cloud. There are hundreds of routers. So when I put tunnel between these two, what happens? E1 will find E2 as just one hop away. So when you run RIP, it will focus only on the hop count and it will choose this path. If I take OSPF will focus on the bandwidth. It may not take the tunnel. Why? Tunnel's bandwidth is always low. OSPF may pick this path whose bandwidth is high, but number of hops are more. It won't use the tunnel. RIP focuses on the hop count. OSPF focuses on the bandwidth. When I enable OSPF, the path taken will not be via tunnel, it will be via the physical path. Assume, E1 has got two paths. One via the tunnel, one via the normal physical layer path, physical path. So when we enable OSPF, it uses the physical path which you do not like. We want the traffic to go via tunnel. So if you enable RIP only, then it is possible. So there is no protocol bad here. There is an assumption that RIP is not good. RIP is who uses RIP. RIP is it's a small product. These are all prejudice. These are all assumptions. Every protocol is important. Fine. Next. Except EIGRP, all the other protocols are well known. EIGRP is Cisco. So you cannot expect EIGRP to be with Juniper. RIP, ISIS, OSPF, BGP is well known. Every vendor knows it. Every router runs it. But the RIP that we learn in Cisco and the one which we learn in Juniper will not be 100% same. Will not. For example, in Cisco, we call something called administrative distance for all protocol. Administrative distance. Juniper also has got something equivalent to that. What is it? Preference. Preference value. The administrative distance is the word that we use in Cisco. In Juniper it is preference value. The administrative distance in Cisco is 120, which is not same in Juniper. 115 for ISIS, 90 for EIGRP, 110 for OSPF. If it is external EIGRP, it is 170. This won't be seen in Juniper. And for RIP, ISIS, OSPF, BGP, it is not the same. In Cisco, IBGP is 200, 20 is EBGP. This is what called as administrative distance. Meaning, using this number, Cisco shows how important is the protocol for that device. The most important protocol for any Cisco device is EIGRP given route. Sorry, not EIGRP, EBGP given route, because the administrative distance is 20. Among routing protocol, most trusted routes are EBGP given routes. If you don't have BGP, then the most relevant, important route is EIGRP given route. Smaller the number, more preference is given. Let's see the preference value in Juniper. So this is what the level, the respect given to the routing protocol, the preference. So what I'm coming to show here is, even though these protocols are standard protocol, industry standard protocol, it's not same. Even if you take Cisco's router RIP, when you enable, the default version that gets enabled is version 1, which is a classful protocol. Whereas in Juniper, it is version 2 by default. You see? So, you got any question?
No.
Alright. Fine. So, protocols are well known, but we cannot say, when we know in Cisco, we cannot say we cannot 100% be sure that we know in the other vendors. There are some variations like this that we need to know before we say yes for another vendor device. Next. So every routing protocol has got an administrative distance. That's what we saw now. Smaller the administrative distance, more preference will be given by the router. The routing table manager will always look into the administrative distance. If two protocols are providing routes, if two protocols are giving routes for same destination, the protocol whose administrative distance is lower, given route will be more prioritized. For example, if OSPF gives a route, EIGRP gives route, but they are not giving the same route. For the same destination 1.1.1.1, OSPF says let's go this way. This is the best path. EIGRP says go this way. Which one should the router receive? Router will receive both, but the routing table manager will compare their administrative distance. Because administrative distance of EIGRP is lower, OSPF given routes will not be honored. In the routing table, only EIGRP route will be seen. OSPF given route will be ignored. It will be there in the database. It will be there in the router's OSPF database, but it won't come to the routing table. Why? OSPF is 110. The lower the administrative distance, more the preference is given. Next. Every protocol has got metric, right? You told me that RIP uses hop count as a metric. Smaller the hop, better is the path. I have two paths, one path with 3 hops, the other path with 5 hops. So the path with the lower number of hops, less number of hops will be given more importance. Likewise, can you tell me what is the metric for EIGRP? Yeah.
Doesn't EIGRP use algorithm or something? That's what I'm thinking of. Suppose.
This is what the metric of EIGRP. It's the slowest link bandwidth plus sum of delay. More detail about this when we get into EIGRP. I'll explain you with a nice picture. But now, as of now, this is what the metric of EIGRP: slowest link bandwidth plus sum of delay. Next, the metric of ISIS. Actually, ISIS do not consider bandwidth nor delay. It works like a hop count only, but not literally hop count. There is a default metric of 10 per link. So if you have 5 links, then it is going to be 50. If you have another path with 2 links, then it is going to be 20. 20 is preferred over 50. So we'll talk about that in detail later when we go there. ISIS has a fixed metric called 10 based on nothing, not based on bandwidth or delay. It's 10 per link. RIP, EIGRP, OSPF. OSPF uses cost. Cost is calculated based on the bandwidth. More the bandwidth, lesser the cost. Lesser the cost, better is the route. That's OSPF. Anything else we left? BGP. BGP never focuses on bandwidth nor hop count. Nothing. BGP only focuses on attributes. We have almost 11 attributes in in BGP. 0 to 11 attributes. When you have multiple paths for a destination, BGP will pick only one path and it will say, for this attribute, I ignore all other paths and I pick only this path. In short, what I want to say is, BGP is not designed to do load sharing. BGP is not designed to do load sharing. It will not do load sharing. So load balancing, load sharing is not at all a topic to be spoken under BGP. In EIGRP, yes, we do speak about equal cost load balancing, unequal cost load balancing. But for BGP, no load balancing. So these things are important when we talk about metrics. We have now spoken about administrative distance in each protocol, metrics in each protocol. Whether it is IPv4 or IPv6, the metrics, the administrative distance, all are same. We have BGP supporting IPv6, likewise OSPF, ISIS, EIGRP, RIP, they all support IPv6. The metric is same for both IPv4 and IPv6. Next. Whatever the routing protocol may be, how much ever powerful it can be, end of the day, the path will be determined by Ceph. Ceph is what going to determine the path. Whether it is BGP given or EIGRP given, that doesn't matter. Ceph will decide the path. Ceph takes the route information from layer 3 and use it in layer 2 level. Ceph is a buffer which is in a layer 2 level with all route information. Layer 2 having layer 3 route info is what Ceph. Cisco Express forwarding. Cisco Express forwarding is the one which decides the path. Switching of packet in a direction. It is a Ceph. More deeper, I will go into more deep dive on these things with a very clear picture when we go to that level. I'm just giving you an idea. You may already know Ceph, so I'm giving more inputs on it, but much more is coming later. Ceph. Now the next thing that we need to know, but you said you are not aware of IPsec VPN, so I'm not getting into that. VPN is nothing but encapsulation. That is what I want to introduce VPN to you. VPN is nothing but encapsulation. Encapsulate. For example, you see we have a computer in 10 network which is connected to a router. This router is connected to a big internet cloud. And here is another router which is having 172.16.0.1 computer. Now this is site 1, this is site 2. This is a private network, this is a private network. If these two need to talk, what we need to have is a tunnel. So what we do is we form a tunnel using the public IP address. Let's say public IP address is 1.1.1.1 here. The address is 2.2.2.2 here, which is already pinging. You see, when we have internet connection, we'll be able to ping from here to here. It's a WAN interface. Using the reachability, we negotiate and we form a tunnel. What does that actually mean? When any packet go from A to B, they cannot be routed in the internet. Why? A and B are in a private network. So when A talks to B, the packet comes up to here with the source address 10.0.0.1, destination address 172.16.0.1. Now what happens when it enters the tunnel? What does that mean? It gets additional layer saying source is 1.1.1.1, destination is 2.2.2.2. Now when packet goes through the cloud only reads this destination. They don't read the inside destination. They read the outside header and they know where to send if it is 2222. 2222 is a public IP address. And packet goes from here to here. This is what called as tunneling. Adding additional layer so that our packet can be routed. Packet cannot be routed with a private IP address. So we add a public header which can be routed and when we send it, the cloud starts forwarding the traffic based on this outer header. We call it as VPN. VPN is nothing but encapsulation. But some people have got a misunderstanding. VPN means security VPN, encryption. No. VPN simply means encapsulating like this and sending so that those unroutable packets can be routed. Any question on what VPN is? Do you have any question on what VPN is?
No, I don't. I just learned something.
Okay. You're clear. Fine. So these are the things that we should know before we get into the very first topic. You're good. If you understand all this, then you're good. So in our next class, we are going to begin from this topic. I'll try to cover the maximum, or at least these 3 topics will be covered. Let me see how it goes. It depends on how many questions you ask and the lab that we do, right? So we stop here.